Everyone, welcome to the video lecture for Unit 3, Module 7.5. And this one, we're going to talk about some of the nuances between gas exchange and gas transport. As always, here are your learning objectives. Be sure to reference these when you're studying for your quiz as well as for the unit exam. Let's go ahead and get started. Pulmonary ventilation ensures that both your alveoli are supplied with oxygen and that the carbon dioxide arriving from your bloodstream is removed. The actual process of gas exchange takes place between blood and the alveolar air across the respiratory membrane. To understand these events, let's first consider 1. The partial pressures of the gases involved, and 2. The diffusion of molecules between a gas and a liquid. Then we can discuss the movement of oxygen and the carbon dioxide across the respiratory membrane. Gases are exchanged between the alveolar air and the blood through diffusion, which takes place in response to concentration gradient. As we saw back in 168, the rate of diffusion varies in response to a variety of factors, including the size of the concentration gradient and the temperature. The principles that govern the movement and diffusion of gas molecules, such as those in the atmosphere, are relatively straightforward. These principles, known as gas laws, have been understood for about 250 years. You've already heard about Boyle's law, which determines the direction of air movement in pulmonary ventilation. In this section, you're going to learn a little bit more about the gas laws and the other factors that determine the rate of oxygen and carbon dioxide diffusion across the respiratory membrane. The air we breathe is a mixture of gases. Nitrogen molecules, or N2, are the most abundant, accounting for about 78.6% of the atmospheric gas molecules. Oxygen molecules, or O2, is the second most abundant and make up roughly 20.9% of air. Most of the remaining 0.5% consist of water molecules, with carbon dioxide, or CO2, contributing a mere 0.04%. Atmospheric pressure at 760 milligrams of mercury represents the combined effects of collisions involving each type of air molecule. At any moment, 78.6% of those collisions involve nitrogen molecules, 20.9% oxygen molecules, and so on. Thus, each of the gases contributes to the total pressure in proportion to its relative abundance. This relationship is known as Dalton's law. The partial pressure of a gas is the pressure contributed by a single gas in a mixture of gases. The partial pressure is abbreviated by the symbol P. A subscript shows the gas in question. For example, if the partial pressure of oxygen is abbreviated PO2, all of the partial pressures added together equal the total pressure exerted by a gas mixture. For the atmosphere, this relationship can be summarized as follows: Pn2 plus PO2 plus PH2O plus PCO2 is equal to 760 milligrams of mercury. We can easily calculate the partial pressures of each gas because we know the individual percentages for each gas in the air. For example, the partial pressure of oxygen, or PO2, is 20.9% of the 760 milligrams of mercury, or roughly 159. The table that you see here, 23-2, includes the partial pressures of other atmospheric gases. Differences in pressure, which move gas molecules from one place to another, also affect the movement of gas molecules into and out of solution. At a given temperature, the amount of a particular gas in solution is directly proportional to the partial pressures of that gas. This principle is known as Henry's law. When a gas under pressure contacts a liquid, the pressure tends to force gas molecules into solution. At a given pressure, the number of dissolved gas molecules rises until an equilibrium is established. At equilibrium, gas molecules diffuse out of the liquid as quickly as they enter it, so the total number of gas molecules in solution remains constant. If the partial pressure increases, more gas molecules go into solution. If the partial pressure decreases, gas molecules come out of solution. You see Henry's law in action whenever you open a can of soda. The soda was put into the can under pressure, and the gas, which is carbon dioxide, is in solution. So when you open the can, the pressure decreases and the gas molecules begin coming out of solution. Theoretically, the process will continue until an equilibrium develops between the surrounding air and the gas in solution. In fact, the volume of the can is so small and the volume of the atmosphere is so great that within a half hour or so, virtually all of the carbon dioxide comes out of the solution, and you're left with what we call flat soda. The actual amount of a gas in solution at a given partial pressure and temperature depends on the solubility of the gas in that particular liquid. In body fluids, carbon dioxide is highly soluble, and oxygen is somewhat less soluble than that. Nitrogen has very limited solubility. The dissolved gas content is usually reported in millimeters per gas per 100 milliliters, or 1 deciliter, of solution. To see the differences in relative solubility of these three gases, we can compare the gas content of blood in the pulmonary veins with the partial pressures of each gas in the alveoli. In a pulmonary vein, plasma generally contains about 2.62 milliliters per deciliter of dissolved CO2, 0.29 milliliters per deciliter of dissolved oxygen, and 0.125 milliliters per deciliter of dissolved nitrogen. Thus, even though the partial pressure of carbon dioxide is less than 1/10 of the partial pressure of nitrogen, the plasma contains more than twice as much carbon dioxide as nitrogen in solution. The gas law is applied to the diffusion of oxygen, carbon dioxide, and nitrogen between a gas and a liquid. We'll now consider how differing partial pressures and solubilities determine the direction and rate of diffusion across the respiratory membrane that separates the air within the alveoli from the blood and alveolar capillaries. As soon as the air enters the respiratory tract, its characteristics begin to change. In passing through the nasal cavity, inhaled air becomes warmer and the amount of water vapor increases. Humidification and filtration continue as the air travels through the pharynx, the trachea, and the bronchial passageways. On reaching the alveoli, the incoming air mixes with the air remaining in the alveoli from the previous respiratory cycle. For this reason, alveolar air contains more carbon dioxide and less oxygen than does atmospheric air. The last 150 milliliters of inhaled air never gets farther than the conducting passageways. It remains in the anatomic dead space of the lungs. During the next exhalation, the departing alveolar air mixes with the air in the dead space, producing yet another mixture that differs from both atmospheric and alveolar samples. Gas exchange at the respiratory membrane is efficient for the following 5 reasons. 1. The differences in partial pressures across the respiratory membrane are substantial. This fact is important because the greater the difference in partial pressure, the faster the rate of gas diffusion. Conversely, if PO2 in the alveoli decreases, the rate of oxygen diffusion into the blood drops. This is why many people feel lightheaded at altitudes of 3,000 meters or more. The partial pressures of oxygen in the alveoli has dropped so low that the rate of oxygen absorption is significantly reduced. 2. The distances involved in gas exchange are short. The fusion of capillary and alveolar basement membranes reduces the distance for gas exchange to an average of about 0.5 microns. Inflammation of the lung tissue or a buildup of fluid in the alveoli increases the diffusion distance and impairs alveolar gas exchange. 3. The gases are lipid soluble. Both oxygen and carbon dioxide diffuse rapidly through the surfactant layer in the alveolar and endothelial plasma membranes. 4. The total surface area is large. The combined alveolar surface at a peak inhalation may approach 140 meters. This area is slightly bigger than half of a tennis court. Damage to alveolar surfaces, which occurs in emphysema, reduces the available surface area and the efficiency of gas transfer. And finally, 5, blood flow and airflow are coordinated. This close coordination makes both pulmonary ventilation and pulmonary circulation more efficient. For example, blood flow is greatest around alveoli with the highest PO2 values, where oxygen uptake can proceed with maximum efficiency. If the normal blood flow is impaired, as it is in pulmonary embolisms, or if the normal airflow is interrupted, as it is in various forms of pulmonary obstructions, this coordination is lost and the respiratory efficiency decreases. Diffusion between the alveolar gas mixture and the alveolar capillaries then increases the PO2 of blood and decreases its PCO2. By the time the blood enters the pulmonary venules, it has reached equilibrium with the alveolar air. Blood departs the alveoli with a PO2 of about 100 and a PCO2 of roughly 40. Diffusion between alveolar air and blood in the alveolar capillaries occurs very rapidly. When you're at rest, a blood cell moves through one of your alveolar capillaries in about 0.75 seconds. When you exercise, the passage takes less than 0.3 seconds. This amount of time is usually sufficient to reach an equilibrium between the alveolar air and the blood. Oxygenated blood leaves the alveolar capillaries to return to the heart, to be pumped into the systemic circuit. As this blood enters the pulmonary veins, it mixes with blood that flowed through the capillaries around conducting passageways. Because gas exchange in the lung occurs only at alveoli, the blood leaving the conducting passageways carries relatively little oxygen. The partial pressure of oxygen in the pulmonary veins therefore drops to about 95. This is the PO2 in the blood that enters the systemic circuit. No further changes in partial pressures occur until the blood reaches the systemic capillaries. Normal interstitial fluid has a PO2 of about 40. As a result, oxygen diffuses out of the capillaries until the capillary partial pressure is the same as that in the adjacent tissues. Inactive peripheral tissues normally have a PCO2 of about 45, whereas blood entering the peripheral capillaries normally has a PCO2 of about 40. As a result, carbon dioxide diffuses into the blood as oxygen diffuses out. Oxygen and carbon dioxide have limited solubilities in blood plasma. For example, at the normal PO2 of alveoli, 100 milliliters of plasma absorbs only about 0.3 milliliters of oxygen. The limited solubilities of these gases are a problem. The peripheral tissues need more oxygen and generate more carbon dioxide than the plasma alone can absorb and transport. Red blood cells solve this problem. They remove dissolved oxygen and CO2 molecules from plasma and bind them, or in the case of oxygen, or use them to manufacture soluble compounds, in the case of carbon dioxide. As these reactions remove dissolved gases from blood plasma, these gases continue to diffuse into the blood, but never reach an equilibrium. The important thing about these reactions is that they are both temporary and completely reversible. When oxygen or carbon dioxide concentrations in blood plasma are high, red blood cells move the excess molecules. When they are falling, the red blood cells release their stored reserves. Each 100 milliliters of blood leaving the alveolar capillaries carries away about 20 milliliters of oxygen. Only 1.5% of this amount is oxygen molecules in solution. The rest of the oxygen molecules are bound to hemoglobin molecules. Recall that hemoglobin molecules consist of 4 globular protein subunits, each containing a heme unit. The oxygen molecules bind to the iron ions in the center of the heme units. Thus, each hemoglobin molecule can bind 4 molecules of oxygen, forming an oxyhemoglobin. This reaction is reversible, and we can surmise it as Hb plus O2 divided by HbO2. This reversible reaction allows hemoglobin to pick up oxygen in the lungs and then release it into the body tissues elsewhere. Each red blood cell has approximately 280 million molecules of hemoglobin. With 4 heme units per hemoglobin molecule, each red blood cell potentially can carry more than 1 billion molecules of oxygen. The percentage of heme units containing bound oxygen at any given moment is called the hemoglobin saturation. If all the hemoglobin molecules in the blood are fully loaded with oxygen, saturation is 100%. If, on average, each hemoglobin molecule carries 2 O2 molecules, saturation is at 50%. In 168, we saw that the shape and functional properties of a protein can change in response to changes in its environment. Hemoglobin is no exception. Any changes in shape can affect oxygen binding. Under normal conditions, the most important environmental factors affecting hemoglobin are 1. The PO2 of the blood, 2. Blood pH, 3. Temperature, and 4. Ongoing metabolic activity within the red blood cells. Hemoglobin in red blood cells carries most of the oxygen in the bloodstream and releases it in response to changes in the partial pressures of oxygen in the surrounding plasma. If the PO2 increases, hemoglobin binds oxygen. If the PO2 decreases, hemoglobin releases oxygen. An oxygen hemoglobin saturation curve, or an oxygen hemoglobin dissociation curve, is a graph that relates the hemoglobin saturation to the partial pressures of oxygen. The binding and dissociation, or release, of oxygen to hemoglobin is a typically reversible reaction. At equilibrium, oxygen molecules bind to heme at the same rate that other oxygen molecules are being released. If the PO2 increases, then more oxygen molecules bind to hemoglobin, and fewer are released. Referring to the equation given in the previous section, we say that the reaction shifts to the right. If the PO2 decreases, more oxygen molecules are released from hemoglobin, while fewer oxygen molecules bind. And in this case, we say that the reaction shifts to the left. Notice that the graph of this relationship between PO2 and hemoglobin saturation is a curve rather than a straight line. It's a curve because the shape of the hemoglobin molecule changes slightly each time it binds an oxygen molecule. This change in shape enhances the ability of hemoglobin to bind another oxygen molecule. In other words, the binding of the first oxygen molecule makes it easier to bind the second. Binding the second promotes binding of the third, and binding of the third enhances binding of the fourth. Because each arriving oxygen molecule makes it easier for hemoglobin to bind the next oxygen molecule, the saturation curve takes the form shown in the image here. Once the first oxygen molecule binds to hemoglobin, the slope rises rapidly until it levels off around 100% saturation. Where the slope is steep, a very small change in plasma PO2 results in a large change in the amount of oxygen bound to hemoglobin or released from the hemoglobin-oxygen complex. Notice that hemoglobin will be more than 90% saturated if exposed to alveolar PO2 above 60. Thus, near normal oxygen transport can continue even when the oxygen content of alveolar air decreases below normal. Without this ability, you could not survive at high altitudes. Conditions that significantly reduce pulmonary ventilation would be immediately fatal. At normal alveolar pressures, the hemoglobin saturation is very high, but complete saturation does not occur until the PO2 reaches excessively high levels, or about 250 or so. In functional terms, the maximum saturation is not as important as the ability of hemoglobin to provide oxygen over the normal PO2 range in body tissues. Over that range, from 100 at the alveoli to perhaps about 15 in active tissues, the saturation drops from 97.5% to less than 20%, and a small change in PO2 makes a big difference in terms of the amount of oxygen bound to hemoglobin. Note that the relationship between PO2 and hemoglobin saturation remains valid whether the PO2 is rising or falling. If the PO2 increases, the saturation goes up and hemoglobin stores oxygen. If the PO2 decreases, hemoglobin releases oxygen into its surroundings. When oxygenated blood arrives in the peripheral capillaries, the blood PO2 declines rapidly due to gas exchange within the interstitial fluid. As the PO2 falls, hemoglobin gives up its oxygen. The relationship between the PO2 and hemoglobin saturation provides a mechanism for autonomic regulation of oxygen delivery. Inactive tissues have little demand for oxygen, and the local PO2 is usually about 40. Under these conditions, hemoglobin does not release much oxygen. As it passes through the capillaries, it goes from 97% to about 75%. Because hemoglobin still retains 3/4 of its oxygen, venous blood has a relatively large oxygen reserve. This reserve is important because it can be mobilized if tissue oxygen demands increase. Active tissues use oxygen at an accelerated rate, so their PO2 may drop to 15 to 20. Hemoglobin passing through these capillaries goes from 97% saturation to about 20% saturation. In practical terms, this means that as blood circulates through the peripheral capillaries, active tissues receive 3.5 times as much oxygen as do inactive tissues. At a given PO2, hemoglobin releases additional oxygen if the pH decreases. The oxygen hemoglobin saturation curve in the image that's shown here was determined in normal blood with a pH of 7.4 and a temperature of 37 degrees Celsius. In addition to consuming oxygen, active tissues generate acids that lower pH of the interstitial fluid. When the pH decreases, the shape of the hemoglobin molecules change. As a result of this change, the molecules release their oxygen reserves more readily, so the slope of the hemoglobin saturation curve changes. In other words, as pH drops, the saturation declines. At a tissue PO2 of 40, for example, you can see that a pH decrease from 7.4 to 7.2 changes hemoglobin saturation from 75% to 60%. This means that hemoglobin molecules release 20% more oxygen in peripheral tissues at a pH of 7.2 than they do at a pH of 7.4. This effect of pH on the hemoglobin saturation curve is called the Bohr effect. Carbon dioxide is the primary compound responsible for the Bohr effect. When CO2 diffuses into the blood, it rapidly diffuses into red blood cells. There, an enzyme called carbonic anhydrase catalyzes the reaction of CO2 with water molecules. The product of this enzymatic reaction, which is H2CO3, is called carbonic acid because it dissociates into a hydrogen ion and a bicarbonate ion. The rate of carbonic acid formation depends on the amount of carbon dioxide in solution, which, as noted earlier, depends on the PCO2. When the PCO2 rises, the rate of carbonic acid formation accelerates and the reaction proceeds from left to right. The hydrogen ions that are generated diffuse out of the red blood cells and the pH of the plasma drops. When the PCO2 declines, hydrogen ions diffuse out of the plasma and into the red blood cells. As a result, the pH of the plasma increases as the reaction proceeds from right to left. At a given PCO2, hemoglobin releases additional oxygen if the temperature increases. Changes in temperature affect the slope of the hemoglobin saturation curve. As the temperature increases, hemoglobin releases more oxygen. As the temperature decreases, hemoglobin holds oxygen more tightly. Temperature effects are significant only in active tissues that are generating large amounts of heat. For example, active skeletal muscles generate heat, and the heat warms blood that flows to these organs. As the blood warms, the hemoglobin molecules release more oxygen that can be used by the active muscle fibers. Red blood cells lack mitochondria. These cells produce ATP only by glycolysis. As a result, lactic acid is formed. The metabolic pathways involved in glycolysis in a red blood cell also generate the compound 2,3-biphosphoglycerate, or BPG. This compound has a direct effect on oxygen binding and release. For any partial pressure of oxygen, the higher the concentration of BPG, the greater the release of oxygen by hemoglobin molecules. Normal red blood cells always contain BPG. Both BPG synthesis and the Bohr effect improve oxygen delivery when the pH changes. BPG levels rise when the pH increases, and the Bohr effect appears when the pH decreases. The concentration of BPG can be increased by high blood pH, thyroid hormones, growth hormones, epinephrine, and androgens. When the plasma PO2 levels are low for an extended time, red blood cells generate more BPG. These factors improve oxygen delivery to the tissues because BPG levels are elevated. Hemoglobin releases about 10% more oxygen at given PO2 than it would otherwise. The production of BPG decreases as red blood cells age. For this reason, the level of BPG can determine how long a blood bank can store fresh whole blood. When BPG levels get too low, hemoglobin becomes firmly bound to the available oxygen. The blood is then useless for transfusions because the red blood cells will no longer release oxygen to the peripheral tissues, even at a disastrously low PO2. The red blood cells of a developing fetus contain fetal hemoglobin. The structure of fetal hemoglobin differs from that of adult hemoglobin, given it at a much higher affinity for oxygen. At the same PO2, fetal hemoglobin binds more oxygen than does adult hemoglobin. This trait is key to transferring oxygen across the placenta. A fetus obtains oxygen from the maternal bloodstream. At the placenta, maternal blood has a relatively low PO2, ranging from 35 to 50. If maternal blood arrives at the placenta with a PO2 of 40, hemoglobin saturation is roughly 75%. The fetal blood arriving at the placenta has a PO2 close to 20. However, because fetal hemoglobin has a higher affinity for oxygen, it is still 58% saturated. As diffusion takes place between fetal blood and maternal blood, oxygen enters the fetal bloodstream until the PO2 reaches equilibrium at about 30. At this PO2, the maternal hemoglobin is less than 60% saturated, but the fetal hemoglobin is over 80% saturated. The steep slope of the saturation curve for fetal hemoglobin means that when fetal RBCs reach peripheral tissues of the fetus, the hemoglobin molecules release a large amount of oxygen in response to a very small change in PO2. Carbon dioxide is generated by aerobic metabolism in peripheral tissues. Carbon dioxide travels in the bloodstream in three different ways. After entering the blood, a CO2 molecule, either 1, is converted into a molecule of carbonic acid, 2, binds to hemoglobin within red blood cells, or 3, dissolves in plasma. All three reactions are completely reversible, allowing carbon dioxide to be picked up from body tissues and then delivered to the alveoli. Let's consider the events that take place as blood enters peripheral tissue, in which the PCO2 is at 45. So the first is carbonic acid formation. Roughly 70% of the carbon dioxide absorbed by blood is transported as molecules of carbonic acid. Carbon dioxide is converted to carbonic acid through the activity of the enzyme carbonic anhydrase in red blood cells. The carbonic acid molecules immediately dissociate into a hydrogen ion and a bicarbonate ion, as we described earlier. But we can ignore the intermediate steps as this sequence and summarize the reaction as CO2 plus H2O transfers into H plus and HCO3. This reaction is completely reversible. In peripheral capillaries, it proceeds vigorously, tying up large numbers of CO2 molecules. The reaction continues as carbon dioxide diffuses out of the interstitial fluids. The hydrogen ions and the bicarbonate ions have different fates. Most of the hydrogen ions bind to hemoglobin molecules, forming the HbH1 complex. The Hb molecules function as pH buffers, tying up the released hydrogen ions before the ions can leave the red blood cells and lower the pH of the plasma. The bicarbonate ion is moved into the plasma with the aid of a countertransport mechanism that exchanges intercellular bicarbonate ions for extracellular chloride ions. This exchange trades one anion for another and does not require ATP. The result is a mass movement of chloride ions into the red blood cells, which is an event known as the chloride shift. About 23% of the carbon dioxide carried by blood is bound to the protein portions of Hb molecules inside red blood cells. These carbon dioxide molecules are attached to exposed amino groups of the hemoglobin molecule. The resulting compound is called carboaminohemoglobin, or HbCO2. We can summarize the reverse reaction as follows. CO2 plus HbNH2 transfers to HbNHCOOH, and we can abbreviate that reaction without the amino groups as CO2 plus Hb transfers into HbCO2. Next is transport in the plasma. Plasma becomes saturated with carbon dioxide quite rapidly. Only about 7% of the carbon dioxide absorbed at peripheral capillaries is transported as dissolved gas molecules. Red blood cells absorb the rest and convert it using carbonic anhydrase or store it as carbaminohemoglobin.